simulate that beta distribution using the concentration parameter and see how values of alpha and beta would change if we change the value of kappa. So mu, I'm going to set it at 0.5, which is the expectation. And the concentration parameter is kappa. I'll call it K. Alpha, we derived, is simply K times mu. Beta is kappa, or K, multiplied by 1 minus Q. Good. So, going to go back to what we did last time. So we have to go back to that previous file. So last time we did the posterior distribution and we used alpha values and beta values, but we kind of used alpha, or not kind of, we used alpha and beta arbitrarily. Here, 118, we tried several different cases. Now, go back to the same. Put it in the top part. Cut the density, which is over here. Get rid of the alpha beta, just make it depend only on the kappa value. So, or kappa and mu. So I'm going to define kappa concentration parameter to be 3. So going to pick kappa to be 3, mu to be 0.5, and sketch the density. Oops. And that's what I get. It seems to be right in the middle. Mu, center 0.5, and concentration seems to be right here. Let's change the value of kappa to 10. Shrinking, right? So if you keep on increasing the value of kappa, 10, 20. So it is becoming more and more concentrated, which is why we call it the concentration parameter. Now, let's go back to kappa of 3, change mu to, let's say, 0.8. Here is a question. Could mu exceed 1? Why not?
Because it's a matter of the mean of the distribution.
It's the mean of the distribution, and the support of beta is between 0 and 1. So its average cannot exceed 1. So mu equals 0.8 constant kappa of 3. That's what we get. And if I increase the concentration parameter, you can see I'm moving it closer and closer to 0.8. So 10, I can change it to 15, 20. But beyond a certain point, I'm just concentrating here. It wouldn't make a difference, so I could even put 200 and see what happens. Fully concentrated, you could put 2000. Right? Eventually, if kappa keeps on increasing, it will simply become a point density, but that wouldn't make sense in our case. So the reason why we call it a concentration parameter is because as we change kappa, we are moving it closer and closer to mu and concentrating around mu. If mu happens to be, say, 0.2, and if I did the same thing, it'll just move to the other side. Yes. So 0.2, and I'm changing the concentration parameter to bring it closer and closer to 0.2. Good. So, previous case, theta is 0.5, sample size, we set it at 1024. We select a random sample of size 1024. And posterior derivation, we did posterior distribution for theta, we did the derivation, and that's what we have. And sample size is quite large. So let's reduce it to maybe 25. And the estimate right now it's about close to 0.3 something. That is the posterior distribution. The actual theta is 0.5. Now, I'm concentrating more toward what value? Which is 0.2. I'm dragging it toward 0.2. Let's see if it kind of moves. I'm going to change kappa from 200 to 2000. Right? Fully moved to one side. So kappa pretty much drove the entire data toward the prior information. Now, if I change the sample size and, make it 2,500 instead of 25, what do we expect to happen if everything went well? Which it never does for us.
Would go closer to the.
It has to move, right? Did it? It did, right? So this is what we mean by a dance between the prior and the likelihood. So either the prior is going to dominate or the likelihood is going to dominate. Our objective is to, get to the right estimate. Large sample size or small sample size, and I don't have a large enough kappa. Last time I believe I used 20. This time I'm just going to use 4. The value that I'm dragging toward is 0.2, so mu is 0.2. Didn't do much. Yes?
Dragged it a little bit.
Drag this a little bit. Let's increase it to 6 and see what happens. Slowly it is moving. Now, if mu is 8, of course it has to go to the other side. Slowly it is moving toward 0.8. And kappa, if I change it to 10, little by little, you are dragging the likelihood toward the prior value that you set. Does that make sense? Okay, now this is the approach where we parameterize based on mu, like the mean. Now we can also parameterize based on the mode, right? So we're just going to change the mean, the expectation, to mode m. And if that is changed, our derivation takes us to m times kappa minus 2 plus 1. That would be the value for alpha. After lots of struggle, we discovered it should be 1 minus m times kappa minus 2 plus 1. When I set mode equals 0.5, it has to be right in the middle. So we set mode equals 0.5. Oops. Same code. All I'm doing is I'm changing alpha and beta and parameterizing using the mode m. Of course, I could have called it as mu. I didn't want to confuse, which is why I called it as m. So that we stick to our derivation. So mode is 0.5 and kappa is 10. So that is the distribution we get. If I move the mode to say 0.9, I just want to plot the density first, nothing else. Moving toward 0.9, mode moved. If I change it to 0.1, the mode is going to move back to 0.1. Yes. Concentration parameter 10. Of course, I put it to say 3. We know what would happen. Yes, it's not concentrated anymore. Now we can go on and run the entire code to determine the posterior. Right now, the value of theta is 0.5 and concentration parameter is at 3. Estimate is at 0.503. Well, that seems way too good to me. So if I change kappa to say 30, shifted toward 0.1. Yes. And if I change the mode to exactly 0.5, which is the value of our estimate 2, it just stays at 0.5 even if the sample size is 25. And if I change it to 0.9, the mode is at 0.9, kappa is at 30. Slight shift. If I reduce kappa to say 5, shifted a bit, right, close to 0.5. That is my sample size. Oops, went to the old code. If I increase the sample size to 2,500, I get 0.5. Now I could make kappa as large as possible. Let's put 50,000 and see what happens. What happened? It went to the prime. So 500, not so much, but you have to have a very large kappa to actually go away from the data and move fully toward the prime. And I don't think in practice people come up with that large of a kappa value. Don't think so. how we did. So what we did today is we know we have a derivation of posterior for Bernoullin probability in terms of beta distribution. All we did today is reparameterize alpha and beta in convenient terms, which is average mu, prior probability for your Bernoullin case, or pick the mode. The mode would be the probability, estimate for your prior probability. So if we picked either the mean or the mode, we can reparameterize alpha and beta, and we can use it in our posterior. Yes? Yes? No, maybe. Is it making sense though? Yes? So in practice, in a situation like that, what are we going to simulate for? In this case, kappa. So we will try to parameterize kappa and simulate for the parameter kappa. But as I mentioned a while ago, it's not just one parameter people will try to simulate and get a posterior estimate. Sometimes we would do both M and kappa. Sometimes kappa could depend on another parameter. So you may have to search through all of them. So that's where we have the standard grid search that we did last time, searching through all possible theta values. That is great and all, but if you have 10 different theta parameters, and you want to search through in a 10-dimensional space so that you want to maximize the likelihood. Is it a good idea?
Sounds like a lot.
It is a lot to do, right? Computationally not feasible, but if we did Gibbs sampling or metropolis sampling, it'll become easier, which is why Bayesian statistics is driven by simulations. Years ago, perhaps 1990 or 1980, when computers weren't that great, these simulations would not have been easy, probably impossible, things that we do today with Bayesian statistics. So computers did make a change.